Hello, my dear students. Welcome to the second part of our lesson about antidifferentiation. Today, we shall focus on finding the antiderivative of a function using substitution method. Furthermore, we shall also be tackling about how to apply the concept of antidifferentiation in solving real-life problems. Specifically, we would like to target the following learning competencies. Compute the antiderivative of a function using substitution rule and solve real-life problems involving antidifferentiation. Before we proceed to our main discussion, let us define three most important words. The first is the word function. A function defines a relationship between a set of inputs and a set of possible outputs, where each input is related to one output. In symbols, we write functions as y equals f of x, where x is an independent variable and y as the dependent variable. Whereas derivative of a function is the rate of change of one variable with respect to another. In symbols, we write dy dx equals f prime of x. Whenever we have a differential equation, we have an equation that defines the relationship between these variables and their derivatives. In symbols, we have dy equals f prime of x dx. In the previous lesson, you have learned the different basic integration formulas and integrals involving trigonometric functions and how these formulas are used in finding the antiderivative of a function. Now, what if we have this kind of expressions or integrand? As you can see, we cannot use directly any of the given integration formulas. We can do some algebraic manipulations in order to find the antiderivative of these functions. In getting the antiderivative of a function by substitution method, we need to remember two important integration formulas. Remember this too, because with this, we would be able to get the antiderivative of the function in a much easier way. Now let's have the first example. We start our solution by letting u be equal to 3 plus x squared. Now getting the derivative on both sides, we will have 2x dx. Now, note that this 2x dx can be seen in the problem. So we can rearrange the terms in the integrand. So we can have 3 plus x squared and then raised to the fifth power 2x dx. Note that 2x dx is equal to du. If we will rewrite this expression in terms of u, we will have u raised to the fifth power du. Now applying the basic integration formula, we have u raised to 5 plus 1 over 5 plus 1 plus c. Simplifying, we will have u raised to the sixth power over 6 plus c. Now let's replace u with 3 plus x squared. So we will have 3 plus x squared raised to the sixth power over 6 plus c. That's the antiderivative of 2x times the quantity 3 plus x squared raised to the fifth power. Now let's have example number 2. We start our solution by rewriting the problem into x times x squared plus 4 raised to negative 1 in order to remove its denominator. Now we let u be equal to x squared plus 4. Then getting the derivative on both sides, we will have 2x dx. However, in the integrand, we only have x dx. So what do? We can divide this into 2. So by cancellation, we can have just 2. So we will have x dx, which is equal to 1/2 of du, or simply du over 2. Now, going back to the main problem, we can rewrite the problem in terms of u. So x dx is 1/2 du, so we can write it, or we can write 1/2 outside the integral sign. And then we have u raised to negative 1 du. Applying the basic integration formula for integrand having an exponent of negative 1, we will have 1/2 times ln, the absolute value of u, plus c. Replacing u with the original expression, we will have 1/2 ln, the absolute value of x squared plus 4 plus c. We start by rewriting the problem. Instead of a radical expression, we will have exponential expression. Now we let u be equal to 5x plus 3. Now to get du, we will have 5 dx. Now as you can see in the integrand, we only have dx. So we divide both sides by 5. So we will have 1/5 du equals dx. So rewriting the problem in terms of u, we will have the antiderivative of u raised to 1/2 du times 1/5. Now applying the basic integration formula, we will have 1/5 times u raised to 1/2 plus 1 over 1/2 plus 1. And then the arbitrary constant c. Now simplifying, we will have 1/5 times u raised to 3/2 over 3/2 plus c. Simplifying further, we will have u raised to 3/2 over 5 times 2 over 3 plus c. Multiply each term, so we will have 2u raised to 3/2 over 15 plus c. Now replace u with the original expression, so we will have 2 times 5x plus 3 raised to 3/2 over 15 plus c. Okay, now what about if we have the Euler number? So we rewrite this in terms of u. So we start our solution with let u be equal to 2x squared. Then getting the derivative on both sides, we will have 4x dx. Now, as you notice, there is 4x dx. So this problem can be written as EU du. So we're replacing the exponent u with the original exponent and then plus c. Now let's have example number 5. We have evaluate the antiderivative of 2x sine x squared dx. Now using the integration rules or the integration formula involving trigonometric functions, we cannot apply any of these rules directly in order to find the antiderivative of the given function. So what we do is to let u be equal to x squared. Now we get the derivative on both sides, so we will have du equals 2x dx. Now, as you can see, we have 2x dx in the given expression. So we can rewrite this expression in terms of u as sine u du. Now, using the integration rules involving trigonometric function, we will have negative cosine u plus c. Now replacing u with the original expression, we will have negative cosine x squared plus c. Now let's have example number 6. Now we choose the expression. Okay, between the two expressions, we will prefer the polynomial with the higher degree. So we will let u be equal to 2x cubed minus x squared plus 2x plus 3. Now getting the derivative on both sides, we will have 6x squared minus 2x plus 2 dx. Now we can reduce by dividing both sides by 2, so we will have 1/2 du equals 3x squared minus x plus 1, which is equivalent to this expression. Take note, we can replace 3x squared minus x plus 1 dx by 1/2 du. Now rewrite the problem using u. So we will have 1/2 of the antiderivative of u raised to the 5th power du. Applying the basic integration formula, we will have u raised to 5 plus 1 over 5 plus 1 plus the arbitrary constant c. So we will have, in the numerator, we will have u raised to the 6th power, whereas in the denominator, we will have 2 times 6, we will have 12 plus c. Now replacing u with the original expression, we will have 2x cubed minus x squared plus 2x plus 3 raised to the 6th power all over 12 plus c. Differential equations may come in different forms, such as what you see on the screen. Okay, this in particular, these are differential equations of order n, which is defined as a differential equation containing a derivative of order n but no other higher derivatives is called a differential equation of order n. The first expression is classified as the first order differential equation, while the second one is the second order is classified as second order differential equation, and the third Since there is, as indicated by this number, we can say that this differential equation is in the first order or in the fifth order. In the previous examples, we were solving for the general antiderivative or the general solution of a first degree differential equation. What about if we have a second degree differential equation? How can we find the function that really, or how can we find the general solution that will satisfy the given condition? Now, to proceed, we integrate both sides, so we will have y prime equals to 3x2 plus 1 over 2 plus 1 plus the arbitrary constant c sub 1. We simplify the first derivative, so the first derivative is equal to, and cancel this, so we will have x plus x cubed plus c sub 1. Now, since you would like to get that function that satisfies the given condition, we integrate further. So y prime would be y equals to x raised to 3 plus 1 plus c sub 1. Simplifying, we will have x to the fourth power over 4 plus c sub 1, c sub 1, c sub 1 x plus c sub 2. Simplifying, hence we will have the general solution. So the function is defined, the original function is y equals x raised to the fourth power plus fourth power all over 4 plus c sub 1 x plus c sub 2. Now, can we find really that particular function that satisfies the given condition y double prime equals 3x squared? Okay. Take note that by adding the condition when c sub 1 equals c sub 2 is equal to 3, what we do is to replace to c x, and then hence the particular solution is y equals 1/4 x to the fourth power plus 3x plus c. Now let me introduce to you separable differential equation. Now take note that a separable differential equation is an equation of the form g of x plus f of y dy dx equals 0, where g of x is a continuous function of the independent variable x alone, and fy is a continuous function of the dependent variable y alone. And this can be written in the form fy dy equals negative gx dx. An example is given below. X squared plus y dy dx equals 0. I guess you're familiar with this form because when we have discussed maximization or related rates, we were able to see addends having dy dx. Now let's try to find the general solution of the differential equation x squared plus y dy dx equals 0. Now we start by writing, of course, the given equation. Then we transpose x squared to the right side to separate the terms having different variables. So we will have y dy dx equals negative x squared. And then we multiply all throughout by dx. So we will have y dy equals negative x squared dx. And then we get the antiderivative of each function. So we will have y raised to 1 plus 1 over 1 plus 1 equal to negative x squared plus 1 over 2 plus 1 plus c. So we simplify, we shall have y squared over 2 equals negative x cubed over 3 plus c. Now we multiply all throughout by 6, so we will have 3y squared equals negative 2x cubed plus 6c. Now rewriting this into standard form of an equation, we will have 2x cubed plus 3y squared equals 6c. Now let's try example number 8. Determine the particular solution of the differential equation dy dx equals e raised to x minus y, satisfying the condition that y equals 0 when x equals 0. To start writing our solution, we copy the function. So dy dx is equal to e raised to x minus y. Now applying the rules on or the law of exponent, we can rewrite the expression at the right side into e raised to x times e raised to negative y. And then we multiply the equation by dx over e raised to negative y. So multiplying dy dx by dx over e raised to negative y, we will have dy over e raised to negative y. When the expression at the right side is multiplied by dx over e raised to negative y, we will have e raised to x dx. Now let's have some manipulation at the left side of the equation. Now, since we have a negative exponent in the denominator, we can rewrite this as e raised to y dy. The negative sign is removed by writing e raised to negative y in the numerator. Now we just copy the expression at the left. Getting the antiderivative on both sides, we will have e raised to y equals e raised to x plus c, which is the arbitrary constant. Now we can transpose e raised to x to the left side, so we will have e raised to y minus e raised to x equals the arbitrary constant. Now since we have y equals 0 when x equals 0, we can replace y and x with 0 in order to find the value of the constant. Now a non-zero number raised to the 0 power is 1. So we will have 1 minus 1, that is 0. So therefore, c is equal to 0. Now writing the particular solution, we will have e raised to y minus e raised to x equals 0. So, or we can also have e raised to y equals e raised to x. This is now the particular solution of the differential equation dy dx equals e raised to x minus y when y is 0 and x equals 0. You might be wondering, where can we apply the concept of antidifferentiation? Today, we shall learn about exponential growth and decay model, which is given by if y is a differentiable function of t such that y is greater than 0 and dy dt equals ky for some constant k, then y equals ce raised to kt, where c is the initial value of y and k is the constant of proportionality. Exponential growth occurs when k is greater than 0, while exponential decay occurs when k is less than 0. Below is an example of a problem involving exponential growth and decay. So let's try. We have life in simple t sub 1/2 is the time required for a quantity of a radioactive material to reduce to half of its initial value. The half-life of a carbon isotope, carbon-13, is 5,715 years. How long will it take for 6 grams of this isotope to decay to 1 gram? We start writing our solution by defining the variables that we're going to use. Let y be the mass in grams of the isotope and t for the time in years. And then the next step is to solve for k in the exponential decay model, which is y equal to ce raised to kt by setting up t equals to 5,715 and c equals 6. Since c is equal to 6, then it will be reduced to 3 by dividing 6 by 2, since the implication of the word half-life means that the quantity of the material is reduced to half of its initial value. And then we replace all the variables with the known values, so we will have 3 equals 6e raised to k times 5,715. Okay, we divide by 6, so we will have at the left side 1/2, and at the right is e raised to 5,715k. And then we get the natural logarithm on both sides. Now we apply the property of the natural logarithm involving the Euler number. So if we have ln e raised to z, then it's just equal to z. So in this case, at the left side, we just copy ln 1/2. At the right, applying the property of the Euler number, and then we will have 5,715k. Now we divide both sides by 5,715. Then using our calculator, k is approximately equal to this very small number. Now using the exponential decay model, we will have the equation y equals 6e raised to the found value of k times t. Now we solve for t when y is equal to 1. Since our goal is to know how long will it take for 6 grams of this isotope to decay to 1 gram. Now we have the equation. If we will have y is equal to 1, we replace y by 1. Then we are ready to solve for t. Dividing both sides by 6, we will have at the left side, the expression would be 1/6. And on the right side, we only have e, which is raised to the value of k and t. Now getting the natural logarithm on both sides, we will have ln 1/6 is equal to ln e raised to the value of k times t, and then applying again this property we will have ln16 equal to 0.00012128555959 times t. And then applying the division property of equality, we would be able to solve for t. And t is approximately equal to 14,773 years. To start with our solution, we define the variables that we're going to use in the solution. We let y be equal to the number of lactobacilli and t equals to time in hours. Now let's have sample problem number 2. Lactobacilli are ubiquitous and normally harmless. In humans and animals, they are found in the intestinal tract and perform many beneficial functions, including immunomodulation, suppression of enteric pathogens, and maintenance of intestinal flora. Like any other bacteria in the culture, it is increasing exponentially. Suppose there are 200 lactobacilli in the culture after 1 hour and 650 lactobacilli after 5 hours. How many lactobacilli are there initially? And then after how many hours will there be? 1,500 lactobacilli in the culture. Just like in the previous example, we have used the exponential growth and decay model, which is y equals CEKT. We will solve for the initial number of lactobacilli, which now we set up y equals 200 when t is equal to 1. Substituting it in the equation, we will have 200 equals CEK times 1. We can simplify further, so the equation would be 200 equals CE raised to k. Now we solve for c by dividing both sides by e raised to k. So on the left side we have 200 divided by e raised to k, while on the right side we have c. So rewriting that, we would have 200 e raised to negative k equals c. That will be our equation or model. Now we solve for k in y equals ce raised to kt by setting up y is equal to 650 and 5 in the equation or the model or our working equation. So we will have 650 equals 200 e raised to k times e raised to k times 5. And then we do some algebraic manipulation. We will have 650 equals 200 e raised to negative k plus k. So applying the laws of exponents. Simplifying, we'll have 650 equals 200 equals e raised to 4k. Simplifying further, we will have 13 over 4 equals e raised to 4k. So we get the ln on both sides. So we have ln of 13 over 4 equals ln e raised to 4k. Okay, now solving for k, we will have ln of 13 over 4 divided by 4, which is approximately equal to 0.29. To solve for the initial number of lactobacilli in the culture, we will solve for c in the equation c equals 200 e raised to negative k. So okay, this is negative, c is equal to 200 e raised to e ln 13 over 4 over 4, which when simplified, it is approximately equal to 149. And then let's answer the last question, which is the number of hours when the population is 1,500. To know the number of hours it will take to have 1,500, we use the exponential growth model. So we will have 1,500 equals 149 e raised to 0.29t. Simplifying that, we would be able to arrive at 1,500 over 49 equals e raised to 0.29t. Now getting ln on both sides, we will have ln of 1,500 over 149 equals 0.29t. Now simplifying further, t will be 7.96. So we were able to answer now all the questions in the problem. Now let's see if you have learned something by introspection with regard to the following competencies: compute the antiderivative of function and then solving real-life problems. Now, if you have questions, please write it in the comment section. I would love to answer those questions, especially if I can.